because we miss out the covariance of the residuals of the parallel mediators. So again, the citation for adding the parallel covariance of the residuals among the mediators is on page 56. It's Pletcher and Hayes, 2008. There's the page number 882. Now, we ran two models. In fact, we call these two models nested models. You will come across of this term very often. You have two models. You have one model, and then you add some parameters. You add some estimated parameters to this model. Then we call this two nested models. Okay, two nested models. So we have one model with more estimated parameters and one model with fewer estimated parameters. So we call this nested models. But the one that has fewer estimated parameters, that means we constrain some of the parameters to zero. Like in our example, we constrain the covariance. In the first model, we didn't estimate the covariance among the residuals. Effectively, what that means is we constrain the covariance of the residuals to zero. So in fact, in the first model, these three are zeros. And in the estimated model, you can see that it is much larger than zero and it is significant. That's why we have a bad fit in the first model. Okay, so in a constrained model, we constrain some parameters to zero. In an unconstrained model, we relax some parameters. Whenever you relax a parameter, your model fit must be improved. Okay, well, maybe the same, but it won't get worse. But then you lose degrees of freedom because you estimated more. In our first model, we say the constraint model is a more parsimonious model because it estimated fewer parameters. In the second model, we estimated 3 more parameters. It is the unconstrained model. Now, we need to justify whether the improvement in fit in our unconstrained model, that means we estimated 3 more parameters, our fit indices improved. Does the improvement in fit justify the 3 more parameters that we estimate? That is what we need to test. This is called a chi-square difference test. So delta chi-square difference is the chi-square of the constrained model minus the chi-square of the unconstrained model. The constrained model is the model that we have not estimated. We have not estimated the covariance. The unconstrained model is the model that we have estimated the free covariance among the residuals of the 3 parallel mediators. And then we have a delta degrees of freedom. We will explain about degrees of freedom tomorrow. Okay, the delta degrees of freedom is the degrees of freedom of the constrained model minus the degrees of freedom of the unconstrained model. Simply speaking, the delta degrees of freedom refers to how many more parameters you are estimating. In our example, we are estimating 3 more parameters in our second model. Therefore, delta degrees of freedom equals to 3. The chi-square for our first model with 5 degrees of freedom equals to 25. The chi-square of the second model with 2 degrees of freedom equals to 1.106. Then we can use this command to find out whether the improvement in fit is statistically significant. Oops. Yeah, sometimes it won't allow me to copy and paste. I think I have that. Yeah, chi-square difference test. If you have not blocked out your R, if your model is still here, then what you can do is like that. And then you will compare the fit of the two models. The second model has 2 degrees of freedom, chi-square is 1.1. The first model has 5 degrees of freedom, chi-square is 25. Chi-square difference is 24, and difference in degrees of freedom is 3. The probability of this is very small. That means the model A1B, the unconstrained model, fits the data significantly better than the constrained model. If you look at this, if you have locked out from R, you lost your 2 models, then it is on our slide 55. Slide 55. Okay. So you can see that the difference in chi-square between the 2 models is 24, and the p-value is very small. That means it's significant. What that means is the unconstrained model fits the data much better, significantly better than the constrained model. So the improvement in fit is much better. This is the concept of nested model, to compare 2 nested models. When you add constraints, whether it will improve or not improve. We will talk more about this on June 17th, Tuesday, when we talk. It is most important when we talk about measurement invariance and measurement equivalence, because we want to test whether the factor loadings and the intercepts are the same, are not significantly different. Then we will add constraints and see whether the model fit will significantly drop. Okay, this is the citation. So what that means is we, out in our first model, we got bad fit. We use modification indices to find out the reason. And then we find out because we miss out covariance of the residuals of the parallel mediators. Here is the citation. That means we should originally add those covariance. What that means is we made a mistake in our first model. Then you can use the same data sets to test your revised model if it is a mistake. If it is not a mistake, if it is missing out a hypothesized path, then you need to collect another set of data to test your new revised model. Have I made myself clear? Am I going too fast?
No.
No objection? Okay. Now, we'll talk a little bit more about mediator and mediating effects. Because in management, in psychology, now, even in marketing, now we have a lot of models that are talking about mediating effect. Sometimes we call them mediating effect, sometimes we call them indirect effect. Mediating effect more referring to conceptual. Indirect effect is more statistical, a statistical term. Okay, but in fact, they're the same. So I will use mediating effect and indirect effect, these 2 terms interchangeably. So what is a mediator? Mediator is a variable which explains the mechanisms through which IV affects DV. So it is trying to answer the question how or why certain effects exist. It is trying to explain how or why your independent variable will affect your dependent variable. It is the objective, major objective of path analysis, of a path analysis. In a path analysis, there are 3 types of effects we can estimate. One is the direct effect, one is the indirect effect, one is the total effect. I don't for those who have heard my presentation before, I don't like the term direct effect. Let me show you this diagram. Okay, we have an X independent variable, a Y dependent variable, and an M, the mediator. Okay, so an indirect effect refers to X go through M to Y. The direct effect is X to Y. However, this effect doesn't really mean that X affects Y directly. What that means is anything that X doesn't go for X on Y doesn't go for M. The effect of X on Y that doesn't go for M. So be very careful when we refer to direct effect. It doesn't really mean that X affects Y directly. It means that any effect X on Y that doesn't go for M. So this, I would usually like to refer this as residual effect more than direct effect, okay? But typically people refer to this path as direct effect. Now we have an indirect effect, we have a direct effect. If we add up the two, that becomes the total effect. C dash is the total effect. So A, for an indirect effect, we simply multiply the paths coefficients. So indirect effect from X to M to Y is A times B. The direct effect is C, so A times B plus C equals to the total effect C dash. Do you understand? Any questions? So how can we test? Typically, our interest is to test an indirect effect. Typically, people will hypothesize like this. X has an effect on, is positively or negatively related to M. M is positively or negatively related to Y. And then the third hypothesis is the effect of X on Y goes to M. So the third hypothesis is a mediating effect. This is a typical way to write your hypothesis. X to M, M to Y, and then the effect of X on Y for M. So when we test the mediating hypothesis, actually we don't care. We don't actually care about the C, the residual effect. When we test, some people says that we should test significant C dash. There is a significant total effect before we can test an indirect effect. It is not true nowadays. It is true when you have such a simple model. But nowadays, a lot of times we have more than one mediator. What if this is positive and other mediator is negative? Then it will cancel out each other. The C dash will be zero. However, it doesn't mean that there's no significant indirect effect. There may be two significant indirect effects. So you don't need to have significant C dash, a significant total effect to test a mediating effect. Now, most of the times we will not hypothesize this C. We will only hypothesize X to M, M to Y, and the effect of X on Y for M. However, even if we do not have this direct path, as I told you this morning, we need to add this direct path here. Why? If we miss out this direct path, then A times B becomes C dash. A times B becomes C dash. That means all the direct effects will inflate A or B, will inflate the AB path. Do you understand? Do you know what I'm talking about? Hello? Hello?
We understand.
Yes,
Okay. You need to give me reactions. I don't know whether you are here. Okay.
Yes.
Now,
Hello, Sam. May I ask one question? Sometimes a model is very complex, have several mediators, have several independent or outcome variables. So if the path C does not significant, can we just remove it?
No, do not remove it. Even though if it is statistically not significant, it is small, but if you remove it, that means you assume this is zero. If you assume this is zero, all the effects still go to AB. Do you know what I'm talking about?
Yes, I know, but I remember maybe 10 years ago. So some journal papers will list several models, then using competing strategies to select a parsimonious model.
No, never.
Okay,
Because that will be sample specific. Okay. Now, here, some scholars, okay, some scholars say that, hey, because you don't have this CPAF in your hypothesis, so you do not need to include this in your estimated model. This is wrong. This is wrong. Why this is wrong? Because if you remove this, that means you're assuming this is zero. All the effects will go to AB. It depends on the direction, whether it is the same as AB. Then if it is, it will inflate AB or it will make AB lower. So always estimate this path. So what is the usefulness of this path? Now, if you estimate AB and then C, in the discussion section, then we will talk about the CPAP. Then we will talk about the CPAP in the discussion. Okay. Now, if your AB is significant, C is also statistically significant. If C is also statistically significant, then we will say that M doesn't. Not all the effects goes through M because there's some significant effect that goes from A to X to Y. Then we will call this a partial mediation. A partial mediation. Only part of the effects go through M. If C is not statistically significant, then we will call this a full mediation. That means all the effects from X to Y go through M. Have I explained myself clearly? That means in the hypothesis, we do not have this path. However, you need to estimate this path because in the discussion, if A times B is significant, then you will interpret whether it is a full mediation or partial mediation by looking at whether C is significant or not. If C is statistically significant, that means there's some remaining effect here, then AB is also only a partial mediation. If C is not statistically significant, that means all the effect will go through M. That is a full mediation. Okay, Xinhua asked the question if we have several serial mediator. Okay, so what direct effect we should add, right? Is that your question?
yes.
I will typically add all the direct effects because I don't know when it will miss. Okay, now give you an example. I think we will talk about this on 17th. Okay. Suppose it's X, ME is time 1, ME2 is time 2, ME3 is time 3, and then finally we will affect dependent variable Y. Does it make sense? Hello?
Oh.
清华
Yes, I'm trying to write down several combination. It seems very complex now.
Now, here, 清华 supposedly your three mediators, now your three mediators, supposedly your three mediators here are the mediator at time 1, then at time 2, then at time 3, and then eventually it will affect y. It happens all the time, okay? Sometimes things take times to happen, right? Then we need to add from x to me2, x to me3, x to y. Well, typically we will not add me1 to me3. You can, and then me1 to y, me2 to y. You get it?
Gordon, I would like to clarify, because there are many different possible direct effects from X to Y, then for this direct effect, should we just only add the direct effect from X to Y?
We will talk about this on the 17th when we talk about post-lag panel model. Post-lag panel model, okay? As I said, okay, for example, you are extending, well, let's say we are a sales outlet, okay? You are expanding your store space, okay? So it will affect your sales in this quarter. In this quarter's sales may affect this quarter's sales and other quarter's sales, and then your profit, okay, at the year end. However, it may also affect the sales in the second quarter and the third quarter before the year end. So we don't know how that happened, but on the 17th, I'm going to show you a cost lag panel model. It can show you all these paths. It is more theoretical, okay? In the cost lag panel model, actually, I will add x to me2, me1 to me3, and me2 to y. That means a lag 2 model. What is your cost for adding all these paths? You lose a few degrees of freedom. You will lose a few degrees of freedom. Your model may look a little bit more complicated, but all these are not big issues. But you won't miss out anything. You get it? But of course, do you really need to add everything? Okay. It is more, I think, I also showed you the paper by Wayne et al. When I talk about interaction effect. You can say what in this particular model, if your me1, me2, and me3 are the same variable at different time points, then I will add x to me2 and x to me3. Do you look at it? I may also add x to y. Now, the question is whether your theory, whether will predict me1 to y. I don't know, okay, about your theory. It very much depends on your variable, whether they are the same variable. If they are not the same variable, then you can just add the direct effect. I will add the direct effect from the very beginning to the end. And then for those in the middle, it depends on whether you can defend. But if you add all the paths, then the reviewers will not say you miss out anything. why don't you estimate all the paths, put the analysis because the model will not too complicated, and hopefully those are not significant, and put it in the supplementary file. You have a simple model. You have a simple model like this, and you put it in the body of the text. You add all the indirect effect, and hopefully if the indirect effects are not significant, put it in the supplementary file. If the direct effects are significant, then you need to put it in the body of the paper. So have I answered your question?
Yeah.
Okay.
Yes, thank you very much.
Yeah. So I'll do 2 sets of analysis. Put 1 set in the supplementary file. Now here, okay. Indirect effect is A times B. Total effect is A times B plus C. Do you all understand what I'm talking about? Now,
Yes.
model fit when the degrees of freedom are 0. Okay, Jinfu suddenly asked me a question about degrees of freedom, model fit when degrees of freedom is 0. When you have 0 degrees of freedom, you cannot evaluate model fit. When you will have 0 degrees of freedom, just like regression. A regression model is a just identified model which has 0 degrees of freedom. When you have 0 degree of freedom, your model always fits the data perfectly. Have I answered your question, Jinfu? Like regression, if you run regression, nobody talks about model fit of a regression model. A regression model always have the perfect fit. Nobody talks about the model fit because you estimated everything already. Okay. So we only look at the estimated parameters. We don't talk about model fit if you have 0 degrees of freedom. Here is how we can create the indirect effect and total effect. Okay, it is based on our previous model. The first part is based on our previous model. And then I added 3 indirect effect. In our model, let me see, wait. Okay. I want to find my model. Yes, this is a model on slide 24. Supervises interpersonal justice to subordinates interpersonal justice. How many paths can it go? How can supervisors interpersonal justice affect subordinates interpersonal justice? We have the first indirect effect that goes through POS is A11 times B11. We have another indirect effect A12 times B21. Another indirect effect A13 times B31. We also have a direct effect C11. That means we have 4 paths. 3 indirect effect, 1 direct effect. The total effect is the sum of all 4. Similarly, for supervisors informational justice, we have A21 times B12. We have A22 times B22. We have A23 times B32, and then we have the C22, 4 paths. So how can we write the syntax? This part I highlighted For the left-hand side of the colon and equal sign means that you create a new parameter. You create a new parameter based on your estimated parameter. A11 times B11, we call it an indirect effect. Supervisor through POS to subordinate interpersonal justice. I just create this name. And then we have A12 times B21 and A13 times B31. The total indirect effect is A11 times B11 plus A12 times B21 plus A13 times B31. This is a total indirect effect. The total effect is the total indirect effect plus the direct effect. C11 is the direct effect. Similarly, for informational justice, we have indirect effect A21 times B12, A22 times B22, and A23 times B32. The total indirect effect is the product term, the sum of the three product terms, and the total effect is the total indirect effect plus the direct effect. So in our model, we extend our original model. This is our original model. By incorporating some new parameters, we actually are not estimating any more parameters. We are just creating some new parameters based on the estimated parameters. So you will find that the model fit will be exactly the same as before. We are not estimating any new parameters. We are creating some new variables which are based on our estimated parameters. So we can run our model again and then ask for the solution. Okay, you can please try to copy and paste this, run this in your R. I think I have the A1C here. Yes, I have the A1C. You have the outcode example A1.txt. This is our example A1C copy. Then I go to R, clear my console, always paste. Oh, that's quick. Fit is exactly the same as our previous model because we are estimating the same number of parameters. What we are doing is, you can see that all the estimates are exactly the same as before. What we have done is in fact creating some new defined parameters. What we have defined here, the indirect effect, free indirect effect, total indirect effect, and the total effect. So you can look at the significance as well, but try not to, okay? I'll explain mine. Have you got your results?
Yes.
Yes, okay. Good. Now, the next concept is how do we test indirect effect? Indirect effect is A times B. The null hypothesis is A times B equals to 0. The software, the R outputs that you have got for the indirect effect, this p-value is what we call a Sobel test. It uses different ways to estimate the standard errors. I think it is the last term. Sometimes some people suggested that we should add a square first term. Some people suggested that we should add the first term. Some people said that we should subtract the first term. Some people said that we do not need to have this first term. Okay, but in any case, the Sobel test S is referring to a T distribution, normal distribution. Okay, it uses a normal distribution. However, even when A is normally distributed, B is normally distributed, A times B is not normally distributed. Therefore, whoever uses the test, they are making a mistake. They assume that A times B is normally distributed. In fact, AB is not normally distributed. So what is the solution? The solution is to use SEM and bootstrapping. Okay, you can blame me, okay, because I published a paper in 2008. This is my second most cited paper talking about using SEM with latent variables to test the indirect effect, and we need to use bootstrapping. In fact, before me, McKinnon and his colleagues, they use regression base and test and show that A times B is not normally distributed. Therefore, they suggest to use bootstrapping. But my paper, the citation is here. My paper says that, well, okay, you better use SEM to incorporate the measurement errors as well. What is bootstrapping? Now, we know that A times B is not normally distributed. In fact, we do not know what is the distribution of A times B. If we do not know what is the distribution of your estimated parameters, the best way we can do is to resample the data many times with replacement to generate a sampling distribution. Instead of relying on the normal distribution or T distribution, we generate a distribution of your estimated parameters. How can we generate the distribution? We in fact assume that you are repeating your study 1,000 times. Each time you find the indirect effect. So now you have 1,000 indirect effect. What you can do is to plot the distribution of the 1,000 indirect effect, and then find out what is the lower 2.5% and the upper 2.5%, or we should say the middle 95% to form the 95% confidence interval. 95% confidence interval. If there's 95% confidence interval does not include zero, then we will say your estimate is significantly different from zero. Okay, this is basically the concept of hypothesis testing. In the past, we rely on a normal distribution and cut the bottom 2.5% and the upper 2.5% to see whether we are falling within the 2.5% or whether the middle 95% include zero. Now we do not have a T distribution or normal distribution to rely on because A times B is not normally distributed. Therefore, we generate this distribution with 1,000 replications. Then we can plot the sampling distribution and find out the 95% confidence interval. Of course, nobody will repeat the study 1,000 times. So what we can do is to rely on the computer. We resample from the data 1,000 times. How can we resample from your sample? Is with replacement. Supposedly, we have five subjects in our sample, A, B, C, D, E. Supposedly, we have A, B, C, D, and E. 5 subjects in our original sample. If we resample a sample of 5 from this, we may have 5 A's, or we may have A, B, C, D, D. We may have B, C, D, E, E. So you will have a lot combinations of resamples. And for each resample, we estimate the indirect effect. course, you don't need to do it manually. It is a very tedious procedure, but it is rather repeating itself. So what we can do is to rely on the computer. Ask your computer to draw the resample and run the SEM model again and collect all those indirect effects. That is what we call a bootstrapping procedure. First, we define a resampling space R, which is typically your observed sample with size n. We generate 1,000 or 2,000 bootstrap samples of size n. And then for each, we estimate your estimated parameters. That means indirect effect here. And then we create the confidence interval. About 15 years ago, is it 15 or almost 20 years ago, when I went bootstrapping, the computers were not that fast. I bootstrapped 200 times. And then computers became faster. I bootstrapped 500 times. And then it became faster. I bootstrapped 1,000 times. The more times you bootstrap, the more points you will have in your sampling distribution, and more accurate is the 95% confidence interval, okay, because it becomes finer and finer. Nowadays, if you bootstrap 1,000 or 2,000 times, which is fine, sometimes people go to 5,000 times. Sometimes people even goes to 10,000 times. They're just showing off how powerful their computers are. It is not very useful. So if you do 2,000 times, nobody will question you. Okay, 1,000 they may question a little bit, okay, but 2,000 nobody will question. There's no need to go to 5,000 or 10,000. Now, there are two ways to create the confidence interval. We can just rank order. We can just rank order the 1,000 indirect effect and cut off the middle 95%. This is what we call a percentile method. Percentile method. There's a more popular method. It's called bias corrected confidence interval. In fact, in 2008, I published a paper with simulations and showing that the bias corrected confidence interval provides you with higher power. Why do we need to have a correction, bias corrected? If you rank order your 1,000 indirect effects, okay, the middle point may not be your sample estimate. Okay? Imagine, recall what you learned about confidence interval from your statistics 101. Okay? How do we build confidence interval for a mean? It is mean plus minus 1.96, which refers to 95%, 1.96 times your standard error. So the midpoint of the confidence interval should be your sample estimate. The midpoint of a confidence interval should be your estimate from the sample. However, if we use the percentile method, the midpoint may not be your sample estimate. Therefore, we have some complicated equations that shifts the curves such that the midpoint is your estimate from your original sample. No matter which way you use, no matter whether you use percentile method or bias corrected method, okay, I think the reviewers will not question. The bias corrected method provides you with a higher power, but people also suggest that we should use percentile method because bias corrected method will inflate your type 1 error. So originally you said a type 1 error, a 95% confidence interval, your type 1 error should be 5%. But in fact, if you use the bias corrected method, it may inflate to 7%. The benefit is that it has higher power. So either way, you can use percentile method or bias corrected method. both are acceptable. In SEM, when we test indirect effect, typically we will do the bias corrected confidence interval. You don't need to worry about all these complicated equations. You do not need to change your model. You do not need to change your model. All you need is when you estimate your model with SEM, you add the bootstrap function in the verb. There are two parts. First, standard error equals to bootstrap. Bootstrap equals to 2000. Okay, so we will estimate our model 2000 times. We can ask for the summary statistics, and then we can ask for the confidence interval. The level equals to 0.95. We want 95% confidence interval, or you can ask for 0.99 and 99% confidence interval. Confidence interval type, we put down BCA.symbol, which means the bias corrected confidence interval. Okay, so if you want to try, you can copy and paste this, or in the model A1D. I have a model A1D here. Copy and paste this. You can see how fast it can run in 2000 bootstrap. Here the console, paste. You can see a circle running. If you use RStudio, you can see a stop sign 2000 times. Oh, what? My computer was fast. It's not as fast as I thought. Oh, I know the reason why my computer is not fast. I've not used my computer. Okay, I got the results. Have you got the results?
Yes.
Good. Well, you have a fast computer too. You can see the three indices are exactly the same, but at the very end, the last part of your output, okay, you should have the confidence interval. I have that, oops. I have that on the slide here. So for the last two columns, you can see CI lower and CI upper, confidence interval lower and confidence interval upper. How can we tell whether a parameter is significant or not? We will see whether 0 fall within these two numbers. I'll show you my R upper here. I have CI lower, CI upper. How can we know if a particular parameter is significant or not? Is we look at these two numbers. Whether 0 falls within this. There's an easy way to tell. If both numbers, these two numbers, have the same direction, that means these are both positive, then it is significant because 0 falls outside. Similarly, this one, it is significant because they have the same positive sign, 0 falls outside. For this, one is negative, one is positive. then it is not significant because 0 fall in between. Do you get it? Then let's look at the indirect effect that we create. The first indirect effect, one negative sign, one positive sign, so it is not significant. This one, not significant. Oh, this is your lucky day. It's 0.00, okay? So this is significant. We got a significant effect from supervisor through anger to subordinate interpersonal justice. It is significant. Do you notice that the p-value, if we look at the Sobel test, it is not significant, but our bootstrapping shows that it is significant. Total indirect effect is significant, the total effect is significant for the informational justice. NA means not applicable. Not applicable. And probably because of the standard error. Do you notice that the standard error is 0? That means there's no variations in the sample. Do you notice that these are all the same? Z value is your estimate divided by the standard error. Because it's 0, it cannot estimate the Z, so it doesn't have the p-value. Okay, and similarly, if you look at the confidence interval, you cannot test it because they are the same. I'm looking at what they are. Supervisor IPJ, supervisor IPJ. Oh, it is the variance of your exogenous variable. This is the covariance of your exogenous variable. It is the variance of your exogenous variable. Okay, so as I told you, we estimate this. Go back to my slide. Go back to my model. Tsinghua asked the question earlier, okay? The covariance of your exogenous variable. Covariance of your exogenous variable. Variance covariance of your exogenous variable. Okay, here you can see that here it doesn't show. If you ask for the SEM output, it doesn't show you. But in fact, we have estimated. It shows in the bootstrap results. Row 24 is the variance. Row 25 is the covariance, and row 26 is the variance of your exogenous variable. This be the reason why they have 0 standard error, because they are inferred from your input data. They are not estimated from the SEM model. They are estimated from your input data. And you won't see any variations here. Now, let me go to this one. Supervisor through POS to subordinate informational justice. Again, it is significant if we use bootstrapping. If you use Sobel test, you can see that it is not significant. Okay. The other three are not significant. The last total effect is significant. Now, do you know how to do the bootstrapping? Find the indirect effect. Do not rely on the Sobel test. If you rely on the Sobel test, it will get rejected, just like what we did in A1C. So what you need to do is in our A1D, we use bootstrapping. Now I use bootstrap equals to 2000, SE equals to bootstrap, and they use the parameter estimates function to show the bias corrected confidence interval. Here, the last two columns. So I also published a paper in 2012 to show people how to compare the effects. In our model, we have three mediators. One typical question is, which mediator is a stronger mediator? That means where will the effects go through? This is our original model. We have the indirect effect and the total effect. Now we can create some differences. We can create some differences. For example, for the interpersonal justice, we can use the POS minus RMI. This is the difference. A11 times B11 minus A12 times B21. Okay. What that means is I want to see whether this path is stronger than this path and this path. We have three indirect effects here. This one, and this one. Which one is the strongest? So we can compare this path with this path, this path with this path, and this path with this path.
您好，
Similarly, for informational justice, we can go from this path. We have three paths, 1, 2, and 3. We can compare this with this. We can compare this with this, and then this with this. So how can we compare? How can we compare? Simple. We just create another new parameter, which is the difference of the two indirect effects. So we added these last 6 lines in our model A1E, the difference between the paths. It is based on our last model, but we add the differences of the indirect effects. Oh, I have that in the file, our code example A1. So I copy and paste all this. And then we also need to do the bootstrapping because it involves indirect effect. Circle is running. Okay, Maxwell asked the question, what is options with equals to 150? Do you notice that for the output for the bootstrap confidence interval, each line has more information? So I want the width to have 150 instead of typically they have about 80. So I can print it smaller. Each line should have 150 characters so that I can have the confidence interval on one line. Okay. Typically, I will do that. I will do that when I have bootstrapping. Running. Okay, I got the result. So our concerns of the last 6 lines, these are the differences between the indirect effects. Only one is significant. Only one is significant. This is for informational justice, the POS and anger. POS and anger. That means A21 times B12 minus A23 times B32. So the result shows that A21 times B12 and A23 times B32 are significantly different. The estimate is positive, okay, A21 times B12. That means going through POS is significantly stronger than going through anger. You got the results?
Yes.
I have a former student. I have a former student who always like to try his luck. Do you notice that? Okay, there are some very, very small. Okay, for example, here, row 27, minus 0.009. Okay, so you just miss. If it is 0.000, then you have significant effect, right? You just miss it. So he asked me whether he can do the bootstrapping again. Yes, you can. Okay, so you can push your luck, increase your bootstrap number of bootstrap samples to see if that will become positive if you have 5,000 bootstrap samples. Okay, bootstrapping is based on random numbers because it draws the sample randomly. But if you have 2,000, it should be very stable already. You can push your luck to see if you increase it to 5,000, this indirect effect, whether it's significant or not. Okay. I want to do the exercise before we take the break. This is a paper based on Zimmerman et al. In 2012 in Journal of Management. It talks about the personality, how it will affect a person's job satisfaction and job search behavior. You can see we have 5 mediators, parallel mediators here. I will call this stage 1 mediator. Job satisfaction is your second stage mediator going to the job search behavior. So here we have 2 mediators. For example, from extroversion going through job search self-efficacy to job satisfaction to job search, we have A12 times B11 times CH1. So the more paths that you go, then you just multiply all the path coefficients. I also add the direct effect here. You can notice that I add the direct effect here. All these paths are based on their hypothesis. I didn't include all the paths. For example, you will see that there is no path from ambition values to job satisfaction because it is not in their hypothesis. If you read the original paper, you will see that it is not in their hypothesis. Now, what I need you to do is, you will find that it is incomplete. Let me see if it is the file that I sent you is also incomplete. Did I send you exercise? No, not this. Yeah. Yes, you should have to file ALCO exercise A1. It is incomplete. Let me solve this. Okay, now ambition here has two paths, A11 times extra plus A21 times neural. So you can see ambition is regression, A11 times extra plus A21 times neural. Self-efficacy, this is A12 times extra plus A22 times neural. This is the reason why labeling all the paths is very important. It doesn't matter what labels you put down, you give them, you just need to create your own system. Now, PJC, perceived job challenge. You will see that there's only one path coming into perceived job challenge. It's A13 times extra. So you need to complete this as A13 times extra. Do you all see what I am doing here? Here, I'm completing this. Burnout only has one arrows going in, so it is A24 times neural. We need to have A24 times neural. Finally, PFI only has one arrows going in, so it is neural. Is A25. A25 times neural. Okay, so I have finished the first part. This 5 extra and neural. The next one is a little bit complicated. Job satisfaction. Job satisfaction. Okay, so how many paths? We have B51 times extra, B11 times self-efficacy, B21 times PJC, B31 times burnout, and B61 times PFI. So it is here already. B11 times self-efficacy, B21 times PJC, B31 times burnout, B41 times PFJ, B51 times extra plus B61 times neural. Similarly, for job search behavior, we have C11 times extra, C31 times ambition, C41 times self-efficacy, C51 times PJC, C81 times job satisfaction, C61 times burnout, C71 times PFI, and C21 times neural. So I typed all this already. Now, do you understand what I'm doing? Each endogenous variable, we have one line, one equation. Okay, so 5 equations, 6, 7 equations. Here we have 7 equations. Then the next step is to covary, because these 5 are parallel mediators. So we need to covary the residuals, just like before. Ambition covary with self-efficacy, ambition covary with PJC, ambition covary with burnout, ambition covary with PFI, etc. So these are all correlated residuals. Then we try to define the indirect effect. From extra to job satisfaction, from extra to job satisfaction, how many paths do we have? We can have the direct path B51. It doesn't go through ambition, but it goes through self-efficacy. So extra A12 times B11. Also, we have A13 times B21. So from extra to job satisfaction, we have one direct path, one indirect path, and the second indirect path. Here, you can see B51 plus A12 times B11 plus A13 times B21. Extra to job search behavior, this is a lot more complicated. Extra to job search behavior, we need to find out all the paths. First, it is C11. And then we can have B51 times CH1. You can also have A11 times CB1, A12 times C41. There's one more. A12 times B11 times CH1, and then A13 times B21 times CH1. You just add all these paths, including all these paths here. Okay, I've done the difficult parts for you. Now, let me see. Self-efficacy to job search behavior. Self-efficacy is here. Job search behavior, it is C41 plus B11 times CH1. C41 plus B11 times CH1. Okay, this is easy part. The next three, that is something that you need to complete. PJC, perceived job challenge to job search behavior, which is C51 plus B21 times CH1. C51 plus A21 times CH1. Now we are working together. Burn out to job search behavior. Burn out to job search behavior. It has C61 is the direct effect, and then BV1 times CH1. So I put down C61 plus BV1 times CH1. And finally, I have PFI to job search behavior. PFI to job search behavior. It is C71 plus B41 times CH1. So we have completed the program. Have you completed the program? Hello?
Yes.
Okay, now let me see where